Okay. Right. So welcome to week number 7. We'll talk about linear regression model today. Okay. So with the in terms of like functionality, in terms of working with R, it's quite simple and easy. But it is good to understand what is linear regression first before getting into the coding part. Okay. So the session will be like we'll have an introduction to linear regression, and then we'll move on to coding that in R. So how to do linear regression in R. So the steps are quite simple in R, so you don't have to worry much about it. Like you don't have to do a lot of coding. And I will just begin with introducing you to linear regression. Okay, and I'll share this PPT later on to your Skype chat. But don't worry, and then you can find similar presentations online anytime. Okay, so let's begin. I'll try to introduce simple linear regression first. And here, so the concept is like I'll talk about a bit of simple regression first, and then I'll move on to linear regression. Okay, so what is simple regression? So simple regression is a kind of a mathematical model that describes relationship between two or more variables. So it is that imagine that you have like multiple variables and you want to find relationship between those two variables, and you need a regression to be performed, right? And imagine, for example, say you have crop growth and you're trying to grow a crop, and the crop growth might be dependent on many other factors, and imagine that can depend on rainfall, right? So you can take a measure of rainfall in a year, and then also like in a month or for like 3 months, and then you can measure the crop growth in the year, and then try to predict whether there is any relationship between availability of water and then crop growth, and that is the base of regression. Okay, and for this, you are supposed to understand one of your variable will be called as an independent variable, which is not really affected by many other factors. But the other one is called as dependent variable, which is affected by many other factors. Okay. So for example, in the example that I told now, the crop growth is dependent on the availability of water. Hence, that is called as a dependent variable. The other case, the water availability is not really dependent on any other things, especially related to the crop growth. Hence, that is called as an independent variable. And what is linear regression? What is the difference from simple linear regression? The simple regression can take many other forms. It can be linear or it can also be curvilinear, and hence linear regression assumes that the regression is kind of either positive or negative, but they are in a straight line, right? Imagine that if you have studied economics, you'll come to know about a concept called as law of diminishing marginal utility. Okay, and that is quite related to your hunger. And if you assume that you are hungry now, and that relationship will be linear with the amount of food that you're trying to take, right? But after eating some food, right? So what happens is that your hunger level will automatically decrease, right? So you cannot really take more, and that happens, right? So for example, say you are hungry and you're going to your dining table, and your mom is ready with imagine dosas, okay? And she gives you one dosa, and you're really happy, and your hunger is kind of sorted out. And then she puts another dosa, then you feel really okay, yeah, that's good, right? And then with the satisfaction of that your hunger will come down a bit. Then again, if you're adding one more dosa, hunger comes down a bit, right? But in terms of if you look the same aspect in terms of satisfaction that you derive from having dosas, right, that would be very different, right? In terms of hunger and then your food consumption, that's kind of linear. But if you take the satisfaction that you derive from having no a dosa, and then if you assume that, right? So imagine that, and also the quantity. So if you're now taking one dosa and you're pretty satisfied with that, right? And then you're taking the second dosa, and then your satisfaction will go higher because you're getting more dosas, right? And you're getting one more dosa, and then satisfaction will also go higher again. But what will happen after your hunger is kind of like um, sorted out, right? So your problem related to your hunger is kind of sorted out, and your mom comes and says like, okay, I prepared like more dosas, right? So you are supposed to take it. And will you be happy to take the fourth dosa after your hunger is kind of sorted out, right? And what happens is that now the regression is like it becomes a more of a diminishing one, or it's like kind of a reduced one, right? And initially the satisfaction peaked up. Now it will start to come down, right? And this is called as a curvilinear relationship, where by adding few more quantities of dosa after reaching your hunger stage, after you sorted out your hunger, and now that becomes a problem again, right? The satisfaction of having one more dosa will come down, and your satisfaction will be in negative phase. Okay, so not all the relationship that you are trying to work with will be linear, right? So there might be different other variations within the regression, right? But today, for the class sake and for the understanding of the basics of regression, we will not worry about the other types of regression like Poisson regression, or like curvilinear regression, or even if you take lasso regression or rigid regression. And there are like multiple other ways in which regression has been computed. Right? We'll not really worry about that, but we'll strictly restrict ourselves to linear regression. We assume there's a simple straight line relationship between those two variables. Right, so I explained you a bit early about what is a linear relationship, what is non-linear relationship, and you can see this one is an example here, right? If it is a kind of straight line, if there's income is increasing, and if people are going to spend more on food, and that's a linear relationship, and that's not really going to happen in the real case, right? So when the income increases, your hunger is not going to change, right? So your food expenditure will increase a bit because you are able to afford to buy more food, but you cannot really eat more. What happens is that there will be a flat line after once you reach a tipping point, and that is called as a non-linear relationship. Okay. And if you're looking at the linear equation, or like linear regression, what happens is that they are actually predicted by a formula called as y is equal to a plus bx. Okay, which was actually thought when you studied your 11th standard, was like nowadays I think probably they introduced to you a bit early, by when you were like at 9th or 10th, but I'm not really sure about it, right? And let's not worry about this plot now, because it talks about the formula, right? And let's go to the formula here first, and then I'll try to explain that one a bit later, right? And the formula is basically where y is your dependent variable, and that is predicted by the independent variable, right? And you may see that there are two other components that is added to it. So one is called as intercept, the other one is called as slope. Okay, and this is the formula. Now it is right time to go back to the graphs that was shown to you earlier. Right? So what happens is that for every change, no, every single unit of change in x, and your y is getting affected. So that's the basic proportion. Right? If there is 1 centimeter increase in rainfall, and how much the crop growth might be affected, right? And that's the base, right? And that is what you're predicting here. So when you have x as 10, and with a straight line, I'm able to find I get 100 units of y, right? So the resultant is like 100, right? When x is 0, I get like 50. When x is 5, and if I want to see, right, I need to draw a line here. If I draw a line from here to on the top, and then what happens is that it should be somewhere around 75 here. Okay, and similarly, you can find what will happen when x is 15. Then you can see it should be somewhere around like 125, right? And typically we found something fishy in the formula, right? So you say like y is equal to a plus bx, right? And we should know what is a, and the a is nothing but when x is 0, and what is the value of y. So that is basically a. And you can see when x is 0 and it is 50, so that's your kind of observation, right? And that's a. And when you want to try to predict what is b, and you can see the formula here says like y is equal to 50 plus 5x. So for every single unit of change in x, there is 5 times effect on y. So that is 5 is given here. Okay, let's also look a bit deeper here in this slide, right? So what it says like every single unit of change in x, and it increases the value of y by 5 times. Okay, so if I have x as 1 and it's going to change, and the resultant y would be like 5. Okay, and that's the base of like an intercept and slope, how that works, right? So this is the y is called as an intercept, and this line here is called as a slope, right? This is a slope. Yeah, so the 1 and 5 depicts the slope, right? And the slope is up here in between, the blue line here. For every single unit of change in your 1, like the x, that results in 5, right? And that is actually captured with this particular uh, triangle here. Okay. Now, so if you want to understand the relationship of any two variables, the first basic ideology is to go for a plot, right? So one way that we can do is like we can go for a scalar diagram, and that is very much applicable for the linear relationship and linear regression. However, there is a kind of a caution as well, right? And if the two data points are continuous in nature, because if they are really numeric in nature, then the scalar diagram will work really fine, right? And in one assumption, the simple linear regression assumes those variables that is taken for the study is continuous, okay, which means it has numbers and it is not basically a categorical data. Okay, so what is categorical data? Imagine if I am going to ask your gender, and you'll say either male or female, or maybe in another category as well, right? So you are put into some silos, and that is actually called as categorical data. But if I ask your income now, and then you will probably throw out a number, it should be like 20, 40, or like 50K per month, and that is actually a continuous data. Okay? So you are supposed to really understand that the base regression is built with an ideology that we are taking two continuous data and try to find relationship between these two data. Okay, and we'll also try to understand least square regression line, least square line a bit later, and we'll also look into that. And similarly, we'll also see what is A, what is B. We had a kind of small exposure to it, but how to really compute that in a statistical way, and that's really important. And also, if time permits, we'll also look at assumptions of regression model. Okay, so now you are back into the formula again. Now you can see a constant term, or called as intercept, and b is the slope, where you saw a small triangle over there, and x is the independent variable which is going to change, and for every unit of change in x, and you will have an effect on y, and that is what we are predicting. So this is the base for regression. Okay. But it is not always that you will have only this, because in real-time scenario, we'll also have something called as an error term added to your formula. So the actual regression model will have y is equal to a plus bx plus an error term. The error term is a kind of is also called as random error term. And why is it happening? Because you cannot, if you say that okay, this is going to be the relationship all the time, and you cannot really end up in the same kind of relationship. Okay, if you look at weather reports, and the weather reports are actually built up based on the regression models, so they take all the possible climatic the weather conditions like humidity, or and then maybe precipitation, and there are multiple other factors that can cause rainfall, right? They'll take all these things. However, like it can, even though if they say that there is like, they'll normally say it's 80% chance of rain, but they will not tell you like 100% chance of rain. Right? And also they'll say like, okay, so there is chance of rainfall and today at like, in the evening, and you may not really get rainfall. So why it did not really happen? Because that's kind of affected by some type of error. Okay, and that is counted here as an error term. So all your models, when you build, will basically have an error term added towards it. Added to it, sorry. Okay. And now we are supposed to find A and B, and we should understand how this A and B is calculated. Okay. And I'm assuming that you all know the basics of like stat, and I'm getting into the slides. Okay. And if you have any questions in between, please stop me. And also, I'm going a bit fast compared to the normal routine. And still, if you have any questions, no, please stop me. Just raise your hand. I was like, just open up your mic and talk to me. Okay. And now let's take kind of data. And this data has like 7 points. And income is captured, and the food expenditure is captured as well. So when the income is 35 and the food expenditure is like 9, so imagine there is like $35 and this is like $9, maybe 35 rupees or 9 rupees. And similarly, this one row is an observation. So this is from one person. This one from person 2, 3, 4, 5, 6, and 7. So they have taken data from 7 different people, and they have uh, captured their characteristics here. Okay, so initially you want to see how it looks in the scatter plot, and you can see they have plotted here with the data that they had, and you can see the data points are like a bit different for each and every household, and but still it throws a kind of a linear regression, right? So it says if you are trying to draw a line from here to like, you are supposed to connect the dots, right? So when you try to connect the dots, and what happens is it doesn't, this line will pass from here and it'll go till here, but it is not really trying to connect all the dots. Okay, so if you're trying to draw a straight line, so which means this is the point for starting to understand where you're having a problem. Okay, and the problem is the error. Okay. And if you try to plot a straight line for each and every data points trying to connect, and for the first observation it will go from here to here. This is one way that you can connect all the dots, and maybe this way you can connect 3 dots, and this way you can basically connect 2 dots. But our idea is to connect all the dots with the least error. Okay, and you can see this is a regression line that was plotted, and which is quite connected 3 dots, right? But it could not really connect other dots, and the difference with the regression line and the dot is called as the error term. So this is the actual value that is observed or captured by the data, and this is the regression line that we built upon, right? And this gap between the regression line and the actual data, or like the predicted line and the actual data observation, is called as error term, right? The idea behind regression is to come out with the regression line that can reduce this error term, right? So you must have the least gap uh, between the observations. Okay, so imagine I'm going to plot a line from here to here, and which means like if it moves from here to here like that, what happens is the error rate for that regression line is going to be higher. Okay, or even if I draw a regression like this, what happens is that still the difference between the actual and then the predicted line is quite really huge, right? And you're not supposed to draw a line like that. Hence, what you are asked to do is like you are supposed to come out with a line which can reduce this the total error that is being thrown out by your prediction. And how can you compute uh, the errors? Okay, so and basically we can compute the error with the error sum of squares. Okay, and that's the difference between the line that you drew with your prediction, right? And and the difference between this line and then the actual observations. Okay, so that is what you called as like y hat. That's your predicted line, and this is your actual observations, and then you're trying to see whether there is any difference. Right? And don't worry about the formula because everything is taken care by R, right? And this is like trying to give you some sort of basics too. And as I told you, right, so in terms of your linear regression, you have the least square regression line. That is what you're trying to see. And you're trying to predict that one. And as I told you, you're supposed to compute A and B. And if you substitute, if you want to find A, what you have is like basically change this moves A towards your left. And what will happen is that A will be equal to y minus no, bx minus y minus bx, right? And this is the formula here. And when it is easy for you to compute A, however, the problem is to compute B. And how will you compute B? And to compute B, you're supposed to find the sum of squared errors of x and y, and sum of squared errors within x. Okay? And how to find SS, or sum of squared error of x and y? And you have a formula here, which says sum squared of errors with x and y is a summation of x and summation of y divided by n. And also you have a summation of x and y minus this particular formula. If you want to find sum squared errors of x with x, and you are saying, say, sum squared of x minus sum squared of sum of x squared divided by n, and this is how you can compute sum of squared of xy and sum squared of xx, and then find the value of b. Okay, and so once you find that, and it will be easy for you to compute a and b. Okay, and now let's get into the data in terms of trying to understand how these things work together. If you have a data point, right? You can see I have value of x and I have value of y, and sum of x should be adding all the data points here in x, and sum of y should be adding all the data points in y, and sum of x and y is multiplying x with y, and then I'm trying to get a value, and then you add all these things, and then I get a sum of x and y. And when I wanted to know sum squared of x, and you basically square x and get information here, and then you sum it up, you add all these row, and you get sum of x square. And you have sum of x, sum of y, and if you want to find the mean of your x and mean of y, and you divide that by the actual observation, that is your n, which is 7, which we know already. And you can see 2 and 2 is from here, and 64 is from here, and they divide that by like 7. So we have like 7 observations. And now we have like 30.28, that's the mean of x, and mean of y is 9.4 and 9.14, which is quite easy to compute within R and with the mean function. Right, and now let's get back to computing b. Right, so in order to compute b, and you're supposed to divide sum squared of xy divided by sum squared of xx. Right, now we have sum of xy, and we know sum of x, sum of y, and sum of and n of it. right? And if you go back to the table, you can see sum of x, y is 2150, so 2150. That is plotted. That is given here, and sum of x is here, and sum of y is 64, and divided by the total observations. Now, the sum of squared of x and y is like 211, and similarly, you can also see sum of squared of x and x is computed by this formula, and we know x squared is here, sum of x squared, substituted here, and you take sum of x, so which is this part, right, and then square it in total, and you divide that by n, and you get like 801. And now if you want to find the value of b, and b is equal to 0.26, and a is equal to y, mean of y minus mean of x, which we computed already, right, minus b, so which means like a is equal to 1.14. And if you substitute this information in the equation that we have, right, so it's like y hat, that's a predicted y, the change in y, right, and this 1.14, which is the value of a, and plus 0.264 of into x, the product of 0.264 and x. So now what we can understand by this equation, but this equation basically says that if in absence of x, and the y value will be like 1.14. But if I add one unit of x, and what will be y? And it's basically a sum of 1.14 plus 0.264, because this is x is basically 1. Okay, and the resultant will be like y is equal to 1.340, something like that, right? And this is what you are going to work on find out. So the basic tenet is to find a value and b value that will produce the least error rate, and that is how this formula to get it out, and we are able to achieve it, with the basic illustration. Okay. And now you can see there's a predicted line of with the formula and with the data that we had, like we predicted that the line predict the straight line and the regression line, and it falls like this here, right? So you can also see it is referred here. So the y hat is equal to y hat is the prediction. So it's a predicted line. So it says here. But now you are supposed to see matched with the actual observations, right? And imagine that the actual observation for some data point is like $900, right? And the predicted line says, okay, it is supposed to be like $1,038, and the difference between the predicted and the actual is called as the error rate, right? If your line has a larger error rate, and basically your model will become insignificant, because your regression line is not fitting really well to reduce the sum of errors, the sum of squared errors. Hence, your model will be insignificant. Okay, we'll have a look into that as well. And now you can see, if you look at the interpretation of A and B, which I told you earlier, but also I'll explain it here. So the interpretation for A is that if there is a zero income, that's the X, if you substitute zero over there, and people will have, they'll spend like $1.14 for their food. Okay. And if there is, but now you can see there's a kind of a change in terms of the degree, because here the interpretation says like it has like 114. So because the data is supposed to be multiplied by 100, hence they just multiplied that by 100 and they gave the result here. So this is supposed to be like $900, $1,500, $700, and similarly the income should be like 3,500 and 4,900 and 2,900. Hence, they just multiply that by 100, and then they put this information here. And later, if you want to look at interpretation for B, as I told you earlier, so for every single unit of change in X, what will be the result of Y? Hence, if there is one person, if like if their income is increased by $1, what happens is their food expenditure will increase by $0.26. Okay, so if you add like $2 to then basically you'll have a 0.26 into 2, and $3 will have like 0.26 into 3, so it will have an effect in such a manner. And it can, like, the linear regression can have basically a positive or a negative relationship, right? Hence you are supposed to be cautious. It is not all the case that you'll have a positive relationship. You can also have a negative relationship. And what can be done, what kind of example we can give, right? So for example, if you take the amount of stress that is you are getting out from your job, right? If it is going to increase, and what will happen to your satisfaction, and basically your satisfaction with the job will decline, and that is what you call as a negative linear relationship. Okay. And one assumption, like, we are getting into the assumptions part of the linear regression, and the assumption one says that we always assume that the random error is not there, or it's like it is zero for every observation of X, but this will not really happen in the real case scenario. Okay, because the basic tenant, or like the basic formula, was built by assuming that the error term is zero. And also the error that you are having when you're trying to build a model, and that error is associated with each and every single observations of X. And the distribution of error, in the sense, this is a bit tricky in terms of understanding from statistics. Okay, so for that, if you want to get to know how this distribution of errors are normal, and you should know some base of statistics, but still I can say maybe in a plain way. So it is supposed to assume normality of no, in terms of, like, your data should have assume normality, and the normality is basically having a bell-shaped curve, which means you do not really have extreme data points. You have a normally distributed data where you have some standard deviation within the limits of 3. Okay, and if you are not getting this point, and I would recommend you to uh, come and attend my statistics class, so that you'll get to know what I'm trying to talk. And similarly, the distribution of the population errors for each of X is same, has the same standard deviation, which is denoted in the standard deviation of your error term, right? And this is a bit tricky again in terms of understanding, right? So it's difficult. But I'll also tell you a few more information which can be taken as an assumption, because that is not really told in this particular assumption slides. Imagine that you're predicting the food expenditure with the data points from 15 to the max of 49. Okay, and what you will try to do is, like, if you're getting a new observation, right? So imagine that he is like earning $20 per month, like $2,100 per month. And then if you want to find this how this guy will spend money, and if you're trying to predict, right? And that's easy. Why? Because your data points, like the model that you built, includes 20 and from the minimum, if you consider the minimum and the maximum, right? So because it starts from 15 and the max is like 49. But if you're trying to predict a person who earns like $10, or it's like 10 like $1,000 per month, and there your model will not work. Why? Because the observation that you had only had a minimum value 15 and the max value is 49. So the range is just like 15 to 49, right? So your model will not be suitable for a person who earns earns like $10, like $1,000. Why? Because it is not really no included in the model. Hence, what you're supposed to do is like you're supposed to include that observation and then try to build a new model. So, and later on, when you have a new data coming in, like maybe like 11 or 12, then you can predict, right? Hence, you're supposed to be cautious when you're trying to apply some models. When you're trying to predict um, some stuff with the existing model, then you're supposed to be cautious. So the maximum and minimum range is supposed to be uh, uh, the new observation should fall into the range which where in which the model was built in. Okay. Any questions in terms of understanding this particular thing? Sorry. Any questions here? Okay, so you can say yes or no in the chat box, then I can move on. Okay. So if the dependent variable is like now we have the dependent variable as a continuous data, right? If in case if the data is not continuous, if it is like just uh, yes or no or something like whether the rain will come today or not, right? So the case of like positive and negative or like true or false, it's kind of a bivariate data, right? In that case, that will get into the stage called as a logic regression. Okay, so which we will see next week. Okay, so now we'll get back into our part and try to understand, because with R you can basically create, uh, get the output in like few seconds, right? So you can predict, you can get a regression line or like a regression equation in like few seconds. Okay, so you don't have to worry about these forms. Okay, so let me share the screen. Okay, so let's get into our studio. Okay. So you are having this RMD file, right? So session 7 for class. Okay, N is missing over there. I hope it's the same over there in your file as well. And use that file and work on the task, right? And if you have any question in the task, just give me a kind of hint. Then I assume that you all know R at the moment, so you will be able to load the CSV file. You will be able to load the packages, and you will also be able to load load the data. And since we have already seen the basics of simple linear regression, just omit that one and but go for this one. Go for the other things. And we'll go chunk by chunk, right? So once you're done with the first three chunks, because that is quite easy, and just put an S, put an S in the chat box. Okay, let me see whether I can create a poll. Oops. Okay, I think I need to edit the poll. uh, like ensure that you are done with the poll, because we just have like 4 people. Hence, it is. I feel it is important that you respond to the poll. Then I can move on to the other task. Like I assume that I was like, if you're struggling with the first 3 chunks, which means like you need to really work on your R. Okay, what sort of problems you might encounter in loading data, right? So ensure that you have your RMD file and your data in one folder, in the same folder, and then you open up the RMD file from the folder so that the path is set, or else you need to set the directory properly. Okay, so when you download these 3 files, it should be in one folder, and from that folder you open up the RMD file and then see the list of files and check where the file is there. Then if you load it, and it will automatically work. Okay, so let me go to the uh, to answers. Okay, so I'm supposed to create an object called a simple.lm and read the dataset read.csv and start apps CSV. Right? I need to execute the code, and now the data is loaded. Yeah, and library dplyr and library ggplot. I hope like we are not going to use so much of dplyr and dplyr today, but still it's better to load it up and then keep it ready. Load that one. Takes a while in my system, so and then you say structure simple.lm. Okay. And if you look at the structure, and you can see RD spend, administration, marketing spend, and you have like 5 variables here. And the 5 variables, we will basically exclude state because that's a character data. You can also work with that one. And if you try to build a model with state, it can also work, right? But it's better to change that as a factor and then store it so that you will get a kind of a proper result. Okay. But for this session, I am not really worried about state data. We'll just skip that one. Right? Let's move on to chunk 4, right? So sorry, chunk 5, I hope. Yeah, so it's chunk 5 in the data, but in terms of task, right? Task wise, it is chunk 4. So in chunk 5, and you are asked to create a sketch plot with the information like R&D spend and then profit. Okay, and try to do that. And for that, you need to load ggplot. Yeah, and I'm not giving any hint here because you're already conversant. I was like, you know how to code and complete the task, and then I think better to put a uh, screenshot of your data in the chat box. Okay. So once you're done with this task, just add a screenshot of your um, chart into the chat box. Okay, got a reply from Anirudhan. Let's have a look into the file. Cheers. It looks really good, right? So we have a scatter plot. Perfect. Glad that you did not include the code. It's I appreciate it, so that nobody's going to copy it. Let's wait for other people to share their screenshots. Okay, Anirudhan, now you can get into chunk 6. Uh, Try to build a scatter plot. Okay, so I had like 3 different scatter plots, but all of them should come in one chart. Okay, so think about using geoms in a proper way, and then do it. No, once you're done with that, just put the chart as the screenshot, like you did now. Okay, so there are a few more chats, a few more. Okay, so think if you cannot send a screenshot, not a problem. You can just say yes in the chat box, okay? And I thought if you can send it, it's okay. Basically, you can just print screen and then save it as a picture. Okay, I got a reply from Naveen, but the chart does not really look like what we expect, right? Think about the geom that you used, Naveen. Right? So you are supposed to see whether you used geom point, right? Yeah, but probably you have used geom bar, right? Think about it, because we need scatter plot, right? So for the scatter plot, and the geom that is used is like geom point. Yeah, perfect, Arun. I got the screenshot. I checked that in. So there is like a distinction between Arun's graph and also from Anirudhan's graph. So what's kind of difference you can see if you are in the Skype window, and what Arun has done is like Arun has used a geom called as geom smooth, right? And then probably he used a method called as method is equal to lm, right? So that is what we will do, right? And that's a part of the next task, right? And I hope I would recommend you to do that as well. So once you're done with this task, just move on to the next task and complete that one. And that's not really tricky, and it's like you need to add geoms, no multiple geoms, and just complete that one. Okay, so I think it's time to reveal the answer for this particular task, and let me go for it. Okay, so there's a reply. Um, Okay. Well, yeah, perfect. Naveen, good. Thanks for your screenshot. Okay, let's get into this particular task and complete this one. So ggplot, and you saw suppose say the data, and it's from simple.lm, okay? And then you need to specify the mapping, that is the aesthetics of it, and say what is going to come in the x and what's going to come in the y, and always x first in the geoms, and profit as the y-axis, and then say geom underscore point, and just leave it blank and execute that. Okay, then you'll get a very good graph. Yeah. So now you should also get this idea, right, in terms of like how to interpret a scatter plot, right? And if you just try to look at the scatter plot now, it looks like a very solid linear relationship, right? As and when the expenditure that you do on your sorry do on your research, and basically your profit is gonna get higher. So the more you spend money on research and development, and basically your startup will earn more. Okay, and that's how any startup can really make money, right? If you look at Elon Musk, he spends a lot of money on R&D, and then he reaps the benefit later on. Okay, now let's look at this part. Okay, so once you are done, this is a bit tricky. For example, say try to add colors to it as well, and try to differentiate with different colors, because everything will now, like if you plot everything in one graph, and every single line and then the dots will be kind of having a black color, and you'll not be able to differentiate. And you can also add color to your scatter plots, right? And the scatter plot with AB line can be achieved with geom smooth. Okay, so try to use geom smooth rather than having, yeah, it's like you must have both of them, geom smooth as well as geom point. So you'll have two different commands for this one. Like in between, if you're finding difficulty in achieving this, like try to inform, try to ask me. Okay, so there's some information in the chat box. Let's have a look. Done with graph using AB line for 3, but the graph does not make sense to me. Okay, if I do not know. Let's have a look into the graph, right? So just put in the chat box, or like put it in you. Okay, so I got one from Anirudhan, right? It's kind of an incomplete plot, but it looks good for me, right? It looks really good for me. So don't worry, we can just work on that and then we can uh, get that ready. Okay. And I'm not really sure how many of like, what happened to other people. Let's have a look at. Can you share your graph, Arun? Like if you have done, did you do the graph separately? And if yes, then don't post it. Right? If you have done, if you are able to plot everything in one graph, then just post it in the chat box. Okay, let's have a look at it. Okay, so it looks good for me. Okay, so just like it needs a bit of additional information. Okay, so we'll do that now. I'll tell you how to do it. Right, so let's if the okay, so let's get back to our studio and try to work with that. Right. Now you need to have a ggplot to initiate the chart, and the data is simple dot lm, right? And then you need to say aesthetics of x is equal to a null, right? And then y is equal to null again, right? Why do I do that? Because I need to add multiple x and y axis, and I'll define that in the geoms, not here. Okay, do you get what I mean? Right? Instead of I'm having an empty chart now, so it will have x-axis, it will have y-axis, but nothing there. So it will not have any data in there. And then I say geom underscore point. I need to get point from say aesthetics of administration profit plus geom underscore point as marketing dot spend profit. So now this will add a geom, the scatter plot, right? But we are ready to add the geom line, like the AB line for it. Okay, and also I need to color it, right? So say color is equal to maybe green, and I say color is equal to blue, and then say geom underscore point and as r dot d dot spend profit, and say color is equal to maybe yellow, because maybe, or it's like pink, because red is quite difficult for me to see. Right? But just look at it, right? Because just look at whether you are getting this one first, right? So now we can see it's differentiated. Basically, you have one the relationship between the marketing spend and then profit is given here, and the R&D and then profit is given here in the pink color. Maybe let's just change that to maybe dark yellow. Let me try whether it is working. Dark yellow is not there. Maybe yellow will be there. Maybe let's have like brown. Right. So let's let that get executed because it's taking much time over there. And then I need to say geom smooth. Yeah. And here still I need to say what is supposed to come in the aesthetics. Okay, AAS. And just copy the code here. Okay. Put it in here. One more specification you need to say is like method is equal to lm. Okay. And recycle this code. then also cycle this code again. But here you were supposed to change that to marketing spend. Dot d dot spend. Okay. Now run this, and once you run this, and your AB line will also be in. Sorry, everything is in green color now. So when you change it, in every places, and run the code. It will take a bit of time because it tries to produce different plots, right? And now you have a very good plot that represents every single variable which is on x and y. Right? You can also add what should come on x and y, but don't worry about that at the moment, like, because you can do that with the labs function, or it's like x lab, y lab function. Right? That's another possibility. Any questions here in this particular stuff? Right. So which one really, which one of this particular relationship, like, is really strong, and which one is really good? If you look at the chart and try to see whether they are really, which one is, which one can turn positive, which one can really predict profitability of the startups. Can you put that in the chat box? Maybe if you cannot talk, you put that in the chat box. Like, say which one of this particular uh, relationship, like you took X, um, like administration, marketing spend, and R&D spend, right? And Arun says it is R&D spend and profit. Yeah. And why do you say so? It's because the errors are pretty narrow. Okay? Because if you look at the error rate of this predicted line, right, so it is really low. But if you look at profit, and it is quite better. Like, it's quite worse than R&D, but it is actually better than the green one, right? So that's from the administration profit. And if you look at the administration profit, right, and maybe you can just mark some of this particular code and then see. Sorry, you need to see the administration, right? And try and find that one. It's alone, right? So just alone. Okay. Oh, sorry. So if you run this code now, and you can see, if you just want to look at that particular data alone, right? And now you can easily observe, right, the data, the error rate is like too huge, right? And the predicted line cannot really estimate the relationship, right? Okay, so I hope you got the nitty-gritty of linear regression now. But now let's get into the actual model. Okay, and because we know how to visualize and see the relationships, but we need to build regression model. Okay, and I'll do one model, that is the simple linear regression model, and the other things are quite easy for you because you are just going to add the variables. Okay, and let's build a model. So model one, and the command for getting building linear model is like lm, which is quite similar to the smooth function that we used, lm, and say what is going to come in the x, what is going to come in the y. Okay, so initially here you are supposed to talk about the y, which is quite similar to the formula that we saw in the slides. Right? You say profit and use a tilde sign, and say r dot d dot spend. Here I did not really mention which one that you were supposed to work, and try with different stuff as well. But here I'll just take the profit using R&D expenditure. and then you define the data. You can say define data is equal to simple.lm, yeah, or else you can just type simple.lm. So that is another option, right? When you assign this model, and it will get executed, right? And what will happen if you just don't do that, right? Think about this one. So what will happen here? It will basically give you this particular output. But I want to get more output from this particular data, because I do not know whether this is significant or not, right? Whether the model is significant or not. And for that, I'll normally assign that entire model to one object. And later, if I type summary of model one, and I'll be able to see the results. Okay. And try this one in your system, and it will work. And okay, so let's wait, right? Now, complete that part, like complete this part, and get this output. And once you have, once you got this output, and say yes in the chat box, then I will proceed in explaining this particular model, because that is really important, right? It's not that just you get output from the models, you should also know how to interpret the output. Okay. Okay. Let's see who has done it. Done. Okay, so we'll have. Okay. So is it good to go with the explanation? Perfect. Okay, so now let's go to the explanation part. Okay, now you can see the formula. The summary gives us the formula that we executed. Right. Basically, it says even if you do not represent what is formula, what is data here, and it produces what you have basically given in the model. Right? So it says the formula is like profit predicted by R&D expenditure, like R&D spent, and then the data is simple LN. Okay, and this the residuals. So the minimum residual, that's the error, right? And so the first and the maximum residual. Okay, so if you plot the data, and you can observe that, right? And one possibility is like you can plot the model one, and you can get it. But let's not worry about that now. Let's just finish this part. And you can see this is the coefficient table. You can extract this coefficient alone, and I'll do that a little bit later. Right now, there are multiple other things here. So one is called as estimates and standard error and t-value. Okay, and don't worry about these two parts. But if you're trying to become a data scientist, and if you want to become a kind of expert in data science, then you are supposed to worry about this. Okay, and t-value is actually derived from this estimate and standard error bar. Okay, the standard error is it's a random error that is a part of your estimate. Okay, part of your model, and the intercept is a. The estimate, you can just refer to the estimate part, right? The 4.903 is the estimate. Okay, that is A in the formula, right? And R&D spent, right? This is B in the formula. So if you want to write the formula, and you're supposed to write the formula like this now. So for example, you are supposed to say profit is equal to 4.903. Like you can convert that E plus into some values. Okay, so just let me put it like that here. And say plus 8.543 E minus 01 into what? It's the marketing spend. So it's like R&D spend, right? R.D spend. So this is the formula, right? So if you spend one dollar, or like maybe in terms of the values of thousands or something, right? And you'll get basically 8.5 times. You'll get a profit of 8.5 times. Yeah. And if you don't even spend any money on R&D, but you'll get some profit like 4.9. Yeah. If you just assume that they are like in tens, and if you spend 1 rupee on R&D, and you'll get 8.5 extra dollars on the profit. Right? If you don't spend any money with the R&D, and you basically get like $4.9. That's going to be your profit, right? Which means it comes from different sources. It can be from a bootstrapping, it can be from something else, uh, maybe from some funding or something like that. Okay, and then we need to also look at some of the other aspects. The last column here in the coefficients table is this is the p-value. Okay, it's called as p-value, and the p-value is supposed to be less than 0.05, and this is the thumb rule, right? This is not this is actually determined by the researcher. Okay. So it is you normally determine that, but at the moment the system basically have a default setting, like it will assume it has a p-value. It should assume that it should have a p-value less than 0.05. Okay, so p-value is a bit tricky to understand, and I'll explain you a bit now, maybe to get an idea. For example, say your company is producing drugs to prevent coronavirus, okay, infection, right? So which means like if you infuse the drug into people, and if there are like 100 patients, and if and they are supposed to recover from that COVID, right? COVID-19. And what happens is that, give me a second, my son is here. Come in like 2 minutes. Just give me 2 minutes. Okay, I'm back. I'm sorry. Okay, so we were talking about like the COVID-19. Right? So imagine that you're getting the drug to 100 people, and then they are supposed to recover, right? So if 100 people recover from that particular by infusing the drug, and which means like you have zero error rate, correct? Right? But if in case, what happens if like 10 people die even after getting your drug, which means like it is having an error rate of like 10%, right? And now this can be equated to the p-value, right? So the p-value basically talks about the error rate that can occur in a model. Yeah. And if the error rate is less than 0.05, it is kind of accepted, right? So imagine if in the medical domain, you don't want everybody to die, right? So if there's like, even you don't want 5 people to die, if you have an error rate of 5%, and if you say that if you infuse the drug to 100 people, and basically what happens is that 95 people will recover, but 5 people will die. So there's a chance that 5% of the people will die, and you don't want to allow more error rate in your model. Okay? Hence, it is for the social sciences, for like sociology and other things, they'll have a error rate of 10 because the behavior of people and then the social level development might be different. Right? But the normal models that we do in psychology and other things, and then we have error rate of less than 0.05%. But for medical conditions, right? So they're supposed to just have error rate of less than 1%, right? And if it is infused to 100 people and then one person will die. But imagine that it's going to be the same case for like 10 million people, right? You infuse that into 10 million people, and if you have an error rate of 1%, it's going to kill a lot of people, right? If you have like, even just to assume that you are going to infuse that to thousands of people, right? So 1,000 people, and if you have error rate of 1%, it's going to kill 10 people out of the 1,000, right? So you are supposed to reduce the error to the least extent in terms of medical research. Right? So the people will set the p-value on their own. So the researchers will set the p-value on their own. Yeah, and it depends upon the researcher's context, but in general, it is set at like 0.5%. And here, and you can see the stars here, like 3 stars, and if 3 stars is here, you can see the error rate is somewhere around 0%. Right? Have a 2 stars occurring here, which means the error rate is like 0.001. Yeah, so it's less than even 1%. And if it is like somewhere around 1%, it'll get a 1 star, and if it is like 5%, it get a dot, and if it is somewhere around 10%, you'll not get anything, it'll get a blank, and at 1, which is like 100% wrong, you will not get anything for that. Okay, as well. The second thing that you're supposed to understand from this output is like something called as multiple R square and then adjusted R square. Okay? And these two are very critical in terms of interpreting your results. Just give me another second. My wife is not at home, and I have to take care of my son. Just give me some time. Sorry about that. Again, like when I was talking about like multiple R squares, so that's a correlation value. So the correlation between these two data. Okay, for example, if you just want to find correlation between these two data, and you can see there's a function called a score, and core of uh, your simple LM and your profit, right? And the simple dot lm of spend dot r dot b dot spend. If you print that one, and you'll basically get the results that is coming here. Okay? Try that on your system and see the results. Okay, so it gets like 0.97, but within the model you get somewhere around 0.9. Yeah, within the model you get like 0.94. Right? But that's the actual reflection that is supposed to be the actual reflection here. That the correlation between these two variables are given as the multiple R square. Okay, and there's a mismatch in the data, but this basically explains the correlation between these two variables. Right? And there is something called as adjusted R square. And the adjusted R square is the actual thing that you're supposed to look in when you're trying to interpret the model. Okay, because the multiple R square is just the correlation between those two variables, but the adjusted R square is the approximation of this relationship to the population, which means when you say that this model can be applied to the entire population, which has the values between no, within the range of x, is the max and minimum range of x, then this shows the strength of the relationship, like strength of your model, right? And this explains it has like 0.94, which means the variance that is occurring in the model is explained in a large way. So it's like 94% of the variation is explained by this model. Okay, which means how can I say about the variance? For example, you have one more variable added to this. Okay, imagine I'm going to do that here. Let's say I want to add administrative cost, administration. So what can happen when I add this variable? Either this can weaken the model or it can strengthen the model, right? So if it is weakening or not, I cannot really understand what's happening behind the screen, right? And for that, this adjust R square will give me an indication. Okay, so let's have a look at it, right? And also the multiple R square will be the correlation of these three variables. Okay, administration. I is missing here. Administration. Expected. Okay, so if you look at the summary of this particular model, and now profit is predicted by two different variables. One is R&D expenditure, the other one is administration. Okay, so if I take a summary of this model, let's wait for it, right? And now you can see this is still, is it the same over here? Let me have a look at it. Let's have like model.2 and say whether it is changing or not, so that we can have a look at it. Okay, so simple.lm summary model.2. Okay, so just remember that we have like 0.959456. That is for model that includes two variables. At one variable, it is now 0.9454, right? So there's a small change in the model, like this R square value, where it moves from, it increases to 0.0002, okay? Right? When it compared to the model one. So if you look at the model one summary, it is 0.9456, which is in addition to the administration cost, okay? And which means like adding administration costs into the model basically explains you more. It explains the profitability more, but it's not at the maximum extent. Okay. Let's also add one more thing. That's a base for the other one. That's multiple linear regression. What we're trying to, when you add more and more variables to it, more and more predictors to it, and that is actually multiple linear regression. Okay. Let's add this for the sake of understanding adjust R square. Okay, so or else like it will be difficult for you to really run through it. Okay, so let's also explain that by marketing dot spend. Say. So now let's have a look at the R square again. Okay, so it's like it moves from 0.9456 to 0.9475. Right, still a subtle change, but it's not really making much difference. So the larger proposed, like the larger variance, like largely your profit is predicted by R&D expenditure because it is significant, right? And because it has 3 stars. And administration and marketing spend, when you add them into the model is becoming better because the R square value increases, and the explanation of your model is good. However, these two variables are not significant, which means they cannot really predict profitability of a startup. Do you get what I mean? Right? So, though they add a little bit of additional explanatory power to the model, but they are not significant. So, don't really use. So, it is better to predict only profitability with the R&D expenditure rather than administration and marketing. Right? Imagine that there is a positive, like there's a significant relationship with administration, right? And if there is like three dots here as well, so what will happen is that administration do also predict profitability, but in a negative way, because you have a negative estimate here, which means as and when your administration cost goes higher, and your profitability will come down. Yeah. And let's not really worry about this F statistics and then other things. Yeah. So what you are supposed to look at is this particular p-value. Yeah. And you'll later understand how this works. Right? And also, you can also perform something called as ANOVA on model.1 and see. I think probably you can see the p-values and other things. Let's wait for it, right? So try that in your system, and if you're getting an output, it will be great to have a look at the ANOVA of the model. Right? So the ANOVA of the model, right? So it basically produces the same table, right? So it's the same table that you got within the summary of the data, right? And still also it basically tells you which one is significant and which one is not significant, right? Out of the models that we had, right? So the model that we had basically had all the information like research expenditure, administration expenditure, and marketing expenditure. And then we just saw these two predictors are not really significant, but this predictor is actually significant. Yeah. And this is really important and critical to understand. Okay. And if you just want to extract the coefficients, like the estimates of your data from the summary, and the formula is coef of model.1. And if you run that one, you'll just extract the estimates that is required, right? But here, basically, it says with the ANOVA table, right? So you basically get sum of square, mean sum of square, and other values that we actually saw in the slide. Yeah. And if you want to extract that, that is if you want that one, then you can do that, right? And this is just the estimates, right? If you just want to write a formula, and the formula will be like this, right? Now, the intercept is 5.01. Yeah, and let's just take the first few digits. 8.5. And it is inappropriate to write these two things because they are not really predicting your profitability, right? And so what I would recommend, like once these things become insignificant, right, I'll remove these two things from the model, and then I'll just retain this model to predict profitability. Yeah? And then just try to get the estimates from that model, and then use that as a formula, right? Because there is no point in adding these two estimates to this particular prediction, right? Because that's not really significantly predicting profitability. Yeah. Any questions here? Can you just respond to the chat, like to the question, like saying yes or no in the chat box? And do you have any questions related to this particular topic in terms of like linear regression, understanding linear regression? Okay, clear. Not at the moment. Okay. Okay. Now let me give you kind of a hands-on. Right? So maybe let's have a look at the plot first, and then move on to the other things. Okay. If you try plot on model 1, okay, this just the plot is just coming from the base base R package, okay, and this is called as residual versus leverage, and don't worry about this plot. Okay? That's what you normally get initially. And this is residual versus footed, and this is like the predicted model versus the actual data. Okay, I think this one is for model 1. Let's try for model 2, because model 2 is significant, right? And you can see the data points are quite near to the estimates. It's like the line that we plotted, right, in terms of the regression line. And if you look at the second graph, so which means the residuals are less here, and why 15, 13, and 50 is coming, these are extreme points. They are kind of outliers. Okay, so if you remove these outliers, and which is like shown here, if you remove these data points from your data, and your model will become better, basically. Yeah. And this is a normal QQ plot. This is called as the normality plot, right? For example, say when I talked about normal distribution curve and other things which is related to that, right? And this talks about whether the data is normally distributed or not. Okay? And as I told you earlier, right? So 37, 15, and 50 are basically extreme outliers, and that is shown here as a number. Right? But apart from that, apart from these three data points, right, other things are quite normally distributed. And how can I understand from that? And if it is near to the dotted line, if the dots are near to the dotted line, which is closely arranged to the dotted line, and which means your data is normally distributed. But if it is slightly no, moving away from the dotted line, like this here, you can see, and which means like there's a little bit of deviation in the normal distribution, but still, if you see a larger deviation like this, right, 15, 50, they are far more deviated, right? And they are not supposed to be they are like kind of having a skew in the data, right? And skewness is talks about the extremeness of your uh, data. Either it is too high in value or it's like too low in value. Okay, and for that you need to understand what is skewness and kurtosis, and that is restricted to the statistics class. Okay, but you can basically understand these graphs now by just also having a look into it, right? And don't really worry about these two plots. They do also have meaning, but they are not really important in terms of understanding your model. Yeah. Okay. So now I will leave it to you in terms of exploring into uh, any other new data. Right. I think I added marketing data.csv in your Skype chat, and think about what kind of model you can build with that particular data. Yeah, take 15 minutes time, and I'll also take a small break, right? And build the model, and then don't worry about plots. Don't worry about plots now. Just build the model and try to interpret the data. And I'll give you like 10-15 minutes. Okay. And if you have any questions, I'll also put it in the chat box. I'll come back in 10 minutes. So we'll meet by 11:50. So in that time, I hope you'll be able to complete the task that is assigned. Okay. So let me also type the task so that you'll be able to do it. Task: use marketing. What's the name of data? It's marketing data. CSV and predict. Build a model. I leave it to you, right, in terms of identifying dependent variables and independent variables, right? Identify TV and IV and build multiple linear regression model. Yeah. And they're like quite easy, and finish it and let me know. Okay, don't put the code in the chat box, but instead say yes or no. I'll be back in like 10 minutes. Okay, so back in, so is the same problem with everyone else? Like, just give it a try. Like, just read the CSV marketing data.csv. Let's have a look at the structure of the data. I think, yep, might be. Mhm. Okay, lazy load. Okay, people are getting different sort of problems. ggplot2. Okay, so I think Swati has a very different issue. So let's so Swati's code is kind of incomplete. Okay, just check, complete the code and then send it to me. Especially you don't have you don't really define the aesthetics part. Okay, and even I have some issues with reading the table, like reading the file. Maybe it is not saved as a kind of let's have whether it's Excel file or CSV file. It's mhm. Okay, so one problem that I can see is that the file is not separated properly, and for example, say it is separated by dot, but not in the case of the headers. When you look at the headers, they are not separated by dot or comma, right? So one thing that you can do is like you can basically rework on this. You can use a structure split command, or like structure remove command from Stringa, and then solve this issue and run the data, right? Is there anyone who got the kind of results from this data set?
Yes, Bala, I was able to read that properly.
Okay, can you share your screen and then we can have a discussion on that? And later people can also work on the data set and then solve the issues, okay? Let me stop sharing and I'll allow you to share. Okay, good. Um, Give me a second. Okay, so now you can share, Venkat.
Yeah.
For like rest of you, you need to maybe I'll clean the file and then put it later on, and you can basically work on that as well. Okay, so let's have a look at the results. So he read the data and then he worked on it. Okay, so let's go for the model. Can you just go to the last model, the multi-linear regression model, your model flag, and execute that, please?
Yeah.
Okay, so now if you look at the data that we got, it's like what we can see is that Facebook is actually predicting the sales and YouTube is predicting sales, but not the expenditure that you are making on newspaper. Hence, Also, the explanatory power of this particular model is somewhere around 0.89, which is really good. And but standard is like it should at least explain 60% of your the variance. Okay. For example, say if the variables that you include in the data in the model should be able to explain at least 60% of the dependent variable. Okay. In this case, it is sales, right? But this model is able to explain at 89%, which means 89% of the variance is explained by this particular model to predict sales. Okay, and what are the other things that we can see? Yeah, which means for this particular, we do not really know what kind of let's see, parameter. Okay, so we may not really know what kind of uh, we don't really know about what kind of business this is, but it is also possible if you know the business better, you'll be able to understand what kind of ads are going to help you to increase sales. Okay, and with this information, we can close this session for the day, and we can talk a bit more on logic regression next week. And if you do not have any questions, you can leave. But if you have any questions, you can stay and then ask me.
One small question.
Yeah.
Could you please say how many sessions do we have? I mean, how many more sessions? Because the
Well,
Zoom session ends by today, the Zoom calendar.
Okay, so I'll add few more sessions. Like I think uh, we should understand logic regression because that is predominantly used in data science area, right? So, for example, say if you're getting whether you to give you a loan or not, or whether you'll pass an exam or not. It's like something else, like whether the person will watch the video or not. So these kind of predictions are actually made with logic regression. So we'll spend 1 week on logic regression, and also we should understand cluster analysis in terms of like segmenting people with the data that we have. For example, say I have a large data set and I want to understand how people are falling into groups, right? Trying to get a similarity. And if you understand these two things, I think it's good to go. So you'll have 2 more sessions. So I'll add that to the calendar.
Yeah,
Okay.
yeah, sure. Thanks.
Yeah, thank you. Anyone else? Any other questions?
Bala can share the PPT and video later. I
Uh,
missed some part of the session today.
yeah, I'll do that. Yeah, sure.
Yeah.
Okay. So anything else? Okay. So if not, I wish you to have a nice weekend. I'll see you next week with logic regression. Uh, have a great day. Bye-bye.
Thanks.
Thanks, you sir. Bye.
Bye. Okay. So, Swati, what kind of problem do you have? Like, I think you are the only one. Okay, Swati left. Not a problem. Let's have a.